Hello everyone, welcome to College Algebra Lecture 5. And in this lecture, we're going to focus on section 2.6 in your textbook, which basically shows you how to solve other types of equations. So the first type of equation that we're going to look at is solving equations involving rational exponents. So solving equations involving rational exponents. Okay, what do I mean by that? Well, I mean that the exponent is a rational number or a fraction. You can think of it as a fraction. So if you have something like a, and let's say the exponent is m over n, so that's a rational number or a fraction. Well, it turns out that the m represents the power of a, and the n represents the root of a. So we can write a to the m over n in several different ways. This is equal to, I can think of it as a to the 1 over n raised to the m, or I can think of it as a raised to the m, and that is raised to the 1 over n. Okay, basically what I'm doing is I'm using one of the exponent rules. Let me remind you of that. Remember, if I have x to the a raised to the b, then the rule is you keep the base x and you multiply the exponent. So it's x to the a times b. So for instance, if I had like x squared to the third power, that would be x to the 2 times 3, which is the 6th. Okay. I can further write these in a slightly different way. Remember that, so let me start with a to the m over n again. Remember, if I raise something to the 1 over n power, where n represents the root, you can think of this as the nth root of a raised to the m, right? So that corresponds to that right there. Or I can do it the other way. I can say it's a to the m, and I'm going to take the nth root of that, which is exactly what this is saying. Okay, so they're just different ways of writing the same thing. Okay, so for example, let's say I want to simplify or evaluate 64 to the negative 1/3 power. Okay, so first thing, remember if you have something raised to the negative, so let me remind you here, I'll do this in red. If I have x to negative a, that's the same as 1 over x to the positive a, right? If I bring the power in from the numerator to the denominator, it changes the sign on the exponent. So the first thing I would do here is I would write this as, this is 1 over 64 to the 1/3. But remember, the 1/3 as my exponent is the same thing as the root with a 3, right? The third root. And what is the cube root of 64? Well, what times what times what gives me 64? That's going to be equal to 4. So 64 to the negative 1/3 simplifies to 1/4 when you work this all out. Here's another example. Let's say I'm asked to solve x to the 5/3 equals 32. Okay, so again, usually when we solve these types of equations, we want to isolate the x, right? We want x by itself so we can just read off the answer. Well, how do I get x? X means x to the 1, right? So how would I get a 1 in my exponent if I have 5/3? What can I do to both sides? Well, what I could do is I could raise both sides to the reciprocal of 5/3, which is 3/5. Right, whatever I do to one side, I have to do to the other side. Why does that work? Because remember, if I use the rule now, or if I multiply exponents, I have x to the 5/3 times, or raised to the 3/5. So I have to multiply 5/3 times 3/5. That's 1. So this is just x, right? I've isolated the x. And in here, probably the easiest way to write this is think of it as the 5th root of 32 raised to the 3rd power. Well, why do I write it like that? Because I know the 5th root of 32, that's 2, right? Because 2 times 2 times 2 times 2 times 2 gives me 32. So this is the same as 2 to the 3rd power. And then 2 times 2 times 2 is equal to 8. So in this case, x is equal to 8. And you can check it, right? You could plug this back in to the original equation, and you'll see, you can think of this as the cube root of 8, which is 2 raised to the 5th power, which gives you back 32. So that works, right? It checks. So x equals 8 is the correct solution. Okay, here's another one. Let's say I want to solve this equation. 3x minus 3 to the 7/3 is equal to 128. Okay, so again, I want to first undo that rational exponent, make it a 1 in some sense. So I could raise both sides do it this way, to the reciprocal of the exponent, which is 3/7. So I have to do the same thing to the right-hand side. Well, that is going to just leave me 3x minus 3 to the 1, right? So I don't even have to write the 1 on the left-hand side. And then I can think of 128 to the 3/7. I can think of it as the 7th root of 128, which happens to be 2 again. And that's going to be raised to the 3rd power. So this is 3x minus 3 equals 2 to the 3rd power. But what's 2 to the 3rd power? That's 2 times 2 times 2, which is 8. So this is just 3x minus 3 is equal to 8. And now I can solve this for x, right? So if I add 3 to both sides, I have 3x is equal to 11, and then divide by 3. So x is going to be 11/3. And that will be my solution. Okay. All right, so I think that's all I want to do with solving equations involving rational exponents or fractional exponents. Let's talk a little bit about solving polynomial equations by factoring or grouping. So let me remind you first. Actually, I'll write this down. So solving polynomial equations by factoring or grouping. We talked a little bit about this earlier as well. So remember, a polynomial equation has the form I'll write it as a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot dot dot, and then it goes all the way down to say x sub or a sub 2 x squared plus a sub 1 x plus a sub 0, and you could even write x to the 0, but we usually don't write x to the 0 because that's just equal to 1. So it's equal to that constant, and since it's an equation, this is equal to 0. Okay, so I want to solve polynomials that have this particular form. So for example, and of course, in this class, you're going to get equations that are, easily solvable by using some of these techniques. In general, it's not so easy to solve, certain polynomials. Okay, so let's say I have this equation, I want to solve it. So let's bring all the terms to the left-hand side first. So I have 5x to the 4th minus 20x squared is equal to 0. And then you should always try to factor out the most you can from every term first before we do anything else. And it looks like here a 5 is common to both terms, right? And an x squared is common to both terms. So I can take out a 5x squared. And I'm left with an x squared, right? Because 5x squared times x squared gives me 5x to the 4th minus 4. And that's equal to 0. Okay, then you need to recognize that the x squared minus 4, that is a difference of squares, right? Remember, if you have a squared minus b squared, that factors into a plus b times a minus b. So that's what we have for that second term. So this is going to factor into x plus 2 times x minus 2. Right? You can think of x squared minus 4 as x squared minus 2 squared. So it's x plus 2 times x minus 2. Okay, and then finally, now I have 3 possibilities, right? I have one possibility is that 5x squared is equal to 0. Another possibility is x plus 2 is equal to 0. And the last possibility is x minus 2 is equal to 0. Well, the first possibility just gives me x is equal to 0, right? I mean, you could formally divide by 5. You get x squared is equal to 0. Then take the square root of both sides, and you're going to find that x is equal to 0. The next one, which is a linear equation, I can subtract 2. So I'm going to get x is equal to negative 2. And then the third one, I can add 2. So x could equal positive 2. So those are all solutions. And you can always plug them back into the original equation to make sure that they work. Okay, what about this equation I want to solve? So this is a third degree, right, polynomial equation. In general, it's not easy to solve this type of equation for x, right? And in particular, we should get 3 values for x. But since we have 4 terms, we can try. There's one technique you can try. If it works, great. If it doesn't work, then you might have to do something else. So let's try solving this by grouping. So we're going to try grouping. And usually if you have 4 terms in a polynomial like that, trying grouping is a good choice. So what do I mean by grouping? Well, I'm going to group the first 2 terms together. By the way, think of minus 9x as plus a negative 9x. So I'm going to group the first 2 terms together and group the last 2 terms together. Now I want to take the greatest factor that I can out of the first group, right, from those 2 terms. So what's the largest thing that goes into x cubed and x squared? It's x squared, right? So I can factor out x squared from that first group. And I'm left with x plus 1. Now my goal is to factor something out of the second group so that I'm left with x plus 1. Is there something I can factor out? Yeah, it looks like negative 9, right? If I factor out a negative 9, I'm left with x, because negative 9 times x gives me negative 9x, and then positive 1, because negative 9 times positive 1 is negative 9. And this is great, because my whole goal is I want these to match here. Okay, why is that? Because now I can factor it out front, right? So I can pull out the 1 plus x all the way out front. And what am I left with? Well, x plus 1 times what will give me this first term? So x plus 1 times what gives me this first term? Well, I'm missing an x squared, right? So I need x squared. And then x plus 1 times what will give me the second term? Well, I'm missing a negative 9. So this is minus 9, and that equals 0. And notice again that the x squared minus 9 is a difference of squares, so I can factor that into x plus 3, x minus 3. Okay, so I'm going to have 3 solutions, right? One possibility is x plus 1 is equal to 0. Another one is x plus 3 is equal to 0. And the third one is x minus 3 is equal to 0. So first one, I can subtract 1. I get my solution x equal negative 1. That's the first solution. I can subtract 3. I'm going to get x equals negative 3. And in the last one, I can add 3. X is equal to positive 3. So those would be my 3 solutions to that equation. So again, try these techniques. It's not always easy to factor, general polynomials, but in this class, you will typically get ones that you can solve, okay? All right, the next type of equation I want to talk about solving is radical equations. So these are basically just the equations that contain square roots, right? Variables on the radicand. So solving radical, let me write that again. Solving radical equations. So first of all, radical equations, I'll give you a definition here. Are equations that contain variables in the radicand. The radicand is the expression underneath the radical, okay? So, for example, if I want to solve, say, square root of t minus 17 minus 4 is equal to 2. How would I do that? Well, the first thing you should do is you should isolate the radical, okay? So to isolate the radical, I need to move that negative 4 to the other side. Okay, I'll say isolate the radical. So how do I do that? Just add 4, right? Add 4 to both sides. So I have the square root of t minus 17 is equal to 6. So I've isolated the radical. Now, remember my whole goal is to solve for t, right? How do I get the t minus 17 out? Well, I can sort of undo the radical by squaring both sides, right? I can square it. So I want to square both sides. Once I've isolated it, I'm going to square both sides. Over here, I'll say square both sides. Okay, so now I just get the t minus 17, right? Because the square sort of undoes the square root. And then on the right-hand side, what's 6 squared? Well, that's 6 times 6, which is 36. And then finally, I can solve for t just by adding 17. And I'm going to get t is equal to 53. Okay. Now, with radical equations, you should always check to see if you got the correct answer by plugging your answer back into the original equation, because when we go ahead and we solve it through that process, sometimes we can introduce answers that were not truly answers. All right, so we should always check by plugging back in. So I'll say it's important to check. I'll do that in red here. It is important to check potential solutions to radical equations, just to make sure you didn't introduce a solution that wasn't really a solution. Okay, so actually here, let's do that for this one. So I have 53, right? I'm going to go back to remember the original equation was this. Square root of t minus 17 minus 4 is equal to 2. So I'll plug in 53 for t. Put a question mark, right? I'm checking this to see if that is true. So what's 53 minus 17? Well, that's 36. And then, of course, the square root of 36 is 6, and 6 minus 4 is 2. So that checks. So therefore, t equals 53 is the only solution, and it's the correct solution in this case. Okay, here's another example. Let's say you're asked to solve the square root of x plus 80 is equal to x plus 8. Well, one nice thing is the radical is already isolated, right? It's already on the left-hand side by itself. So now I'm going to simply square both sides. So left-hand side is simply going to give me x plus 80. Right-hand side, remember what this means, right? If I have x plus 8 squared, that's the same thing as x plus 8 times x plus 8. So you could either remember there is a formula if you square a sum, but it's easier just to FOIL this out, right? Because we know it just means x plus 8 times x plus 8. So if I FOIL this out, I multiply this out, I'm going to get x squared plus 8x plus another 8x plus 64. So this is going to be x squared plus 16x plus 64. Okay, so this side is x squared plus 16x plus 64. Okay, so now, well, it looks like now I have a quadratic, right? So I need to get everything to one side, and I want to keep the x squared term positive, right? The coefficient positive, positive 1. So in this case, I want to bring everything to the right-hand side. So I'll subtract x. I'll do all at once and subtract 80. So subtract x, subtract 80. And I'm going to get 0 is equal to x squared. Then 16x minus x is plus 15x. And then 64 minus 80 is a negative 16. Okay, if you want, you can even write it like this if you want to write it on the left-hand side. It doesn't matter. Okay, so now I have a quadratic equation again. How do I solve this? Well, we can use all of our different techniques. I would try factoring because it's the quickest if it works. If not, then you might have to go to the quadratic formula or completing the square. But try factoring first because that's the easiest if it works. So if I try factoring this, well, I'm looking for two things, right? When multiplied, give me negative 16, and added, give me positive 15. Well, I guess 16 and 1 will work, right? Actually, 16 and negative 1, right? So if I do positive 16 and negative 1. So if I multiply those, 16 times negative 1, I get negative 16. If I add them, I get positive 15. So that works. So one solution, potentially, remember we need to check this at the end, is x is equal to negative 16. And then the other potential solution is x is equal to 1. Okay? So if I go back and I check these, actually I know that negative 16 can't be the answer, right? Because remember my original equation was x plus 80 equals x plus 8. So if I plug in negative 16, I have negative 16 plus 80 is equal to negative 16 plus 8. But then this says that this is what, 64? So square root of 64 is equal to negative 8. Well, I know that the square root can't be negative, or even if you want to go further, you could say you get 8 is equal to negative 8. That's not true, right? So therefore, this is actually not a solution. So this was our potential solution. It is not a solution. Let's try the other one. So if I plug in x equals 1, I get 1 plus 80 is equal to 1 plus 8. So this is a square root of 81, which is equal to 9, and square root of 81 is 9, so that works. So this is our only solution in this case, x equals 1. Sometimes you have multiple solutions, sometimes you only have one. Actually, sometimes you could have no solutions. You need to check them. It's really important that you check. Okay, what if we have something slightly more complicated where we have multiple radicals within the equation? So let's say, I'll go to a new page for this. Let's say I want to solve square root of m plus 1 is equal to square root of m plus 13. Okay, so what you want to do is you want to isolate one radical first. And in this case, actually, I do have one radical isolated. It's isolated on the right-hand side, right? So you isolate one radical. Doesn't matter which one. So that step is already done. Now what I can do is I can square both sides. So actually, I'm going to write it like this. I'll just put this one, the isolated radical on the left-hand side. Okay, now I'm going to square both sides. The whole thing. Be careful, I want to square the entire right-hand side. So the left-hand side just gives me m plus 13. But the right-hand side, again, you have to work this out, right? You have to FOIL this out. This is really the same as square root of m plus 1 times itself. So if I multiply square root of m times square root of m, well, that's equal to m. Square root of m times 1 is plus square root of m. 1 times square root of m is another square root of m. 1 times 1 is 1. So this is m. Square root of m plus square root of m, those are sort of like light, you can think of them as like terms. So I have 2, right? Radical m, or square root of m, plus 1. So this is going to equal m plus 2 square root of m plus 1. Okay, now what? Now isolate the second radical. So at this step, you want to isolate the second radical. So let me write it in here. So I have m plus 13 equal to m plus 2 radical m plus 1. So now isolate the second radical. Okay, so how do I get that radical by itself? Well, I need to get rid of the m, so I'll subtract m from both sides, and the 1. Well, this is kind of nice. The m's disappear, right? And I just end up with 12 is equal to 2 radical m. And if you want, you can even get rid of the 2. Let's just do that. I'll divide by 2. So I'm going to get 6 is equal to radical m. And now what do you think that we're going to do? We're going to square both sides again, right? Actually, let me write the radical on the left. So I'll square both sides. So I get m is equal to 36. So that's my potential solution. Let's check it. So I go back to the original equation, which was this. And I plug in 36. Let's see if it works. So I have square root of 36 plus 1 equals square root of 36 plus 13. So this is 6, right? Plus 1. This is a square root of, what's that? 49, which is 7, right? So this is 7 is equal to 7. So that checks. So that is my solution. So m equals 36 is the correct solution in this case. Okay, and I'll do more of these during the lecture when we meet in class. Okay, let me talk about two more topics for this section. One of them is solving an absolute value equation. Okay, so what is the absolute value equation? Well, remember, if we use two vertical bars, that represents the absolute value of x. And formally, we can define it as a piecewise, what's called a piecewise function. It's equal to x, right, just equal to itself, if x is greater than or equal to 0, if it's non-negative, or it's equal to negative, the opposite of itself, if x is less than 0, right? Or you could also think of it as defined in terms of the distance from 0 on a real number line. Okay, you could also say, all right, this way. Absolute value of x is the distance from 0 on a real number line. So, for example, let's do a couple of quick examples here. Let's say I want, to find the absolute value of 4, right? Well, on a real number line, here's 0, right? Here's 4. What is the distance from 0? How far is 4 away from 0? Well, it's 4 units away. So absolute value of 4 is simply equal to 4, right? If I wanted to know absolute value of negative 3, then I would go to negative 3. How far is it away from 0? Distance, remember, is always non-negative. It could be 0, but it's typically positive, right? It's always non-negative. I just want to know how far away I am. Well, I'm 3 units away. So in this case, absolute value negative 3 would be positive 3. Okay, so basically, if the original number is positive, it stays positive. If it were negative, it becomes positive. Okay, and that fits with this first definition too. We'll talk more about piecewise functions later when we get into functions. For now, just think of it as a distance from 0 on a real number line. Okay, so there's basically going to be 3 possibilities when we solve an absolute value equation. So first possibility, if c is less than 0, then if I have an absolute value equation that says absolute value of ax plus b equals c, this is going to have no solution. Has no solutions. Why? Well, let me just make an example. Let's say I have absolute value of 3x, minus 2, right? That's my expression inside the absolute value. And then c is less than 0, so let's say it's like negative 5. Well, can an absolute value ever be negative? Could it be negative 5? No, right? There's no solution to that because the absolute value cannot be negative. Okay, another possibility. If c, and just these all depend on c, if c equals 0. So then I have, say, absolute value of ax plus b equals c. It's going to have one solution. And in fact, if it equals 0, then that means what's inside, right? What's inside the absolute value must also equal 0, right? Because the only way I can get 0 is if I take the absolute value of 0. That gives me 0. So if c is 0, that means whatever I have inside must equal 0. So for example, let's say I have, here I'll just use 3x minus 2 again. If I have 3x minus 2 is equal to 0, then the only way that can be true is if the expression inside is equal to 0. So I could set it equal to 0 and then solve. Right, I could add 2, so I have 3x is equal to 2, and then divide by 3. So x is equal to 2/3. That would be my solution. So it has just one solution. Okay, and then if c is positive, if it's greater than 0, then there's going to be 2 solutions. So if c is greater than 0, then the absolute value of ax plus b equals c has 2 solutions. So again, why is that true? Because let me just explain it with an example. Let's say I have, I don't know, 2x plus 4 is equal to, say, 8, right? Well, in order to get 8, that means that this expression inside could have been an 8, right? Because absolute value of 8 will give me 8. Or it could have been a negative 8, right? Because absolute value negative 8 also gives me 8. So I have to try both of them. I have to set my expression equal to 8 in solve, and I have to set it equal to negative 8 in solve. They're both going to be possible solutions. So in the first case, if I work this out, this would be 2x is equal to 4, right? Divide by 2. So x is equal to 2. In the second case, subtract 4, I'm going to get 2x is equal to negative 12. Divide by 2. X is equal to negative 6. And there's two solutions. These will both cause the expression inside to be 8 or negative 8. And then when I take the outside value, I get positive 8. So it checks. All right, so let's do a few more examples here. Let's say I want to solve x plus 4. So absolute value of x plus 4 is equal to 6. So since the right-hand side is larger than 0, greater than 0, there's two possibilities, right? X plus 4 could equal 6, or it could also equal negative 6, right? Because in both cases, if I take the absolute value, I'm going to get positive 6. So in the first case, my solution is going to be x is equal to 2. And in the second case, so or x is equal to, looks like negative 10. Right? I get two answers for that. Okay, how about this? Solve absolute value of 2x minus 3 is equal to negative 8. Well, again, if you look at this, can an absolute value ever be equal to a negative value? No, right? So immediately we say there's no solution. Right? And the reason is the absolute value of 2x minus 3 can't be negative. The smallest it could be is 0, right? It can't be negative. So immediately there's no solution. Okay, what about this? How do I solve this? Well, I really want to isolate the absolute value first, right? So I'll say isolate the absolute value term. Okay, so how do I do that? Well, I need to get rid of that 4 first. Let me just write this over again. So I need to subtract 4 from both sides. So I have 6 times 6x minus 6, and the absolute value is equal to, I guess it's 36. Then I need to get rid of the 6, so I'll divide both sides by 6. Right, that'll give me 1 times, so now basically I've isolated my absolute value term. And of course the right-hand side, what's 36 divided by 6? That's 6. And now, remember there's two possibilities, right? Since the c is positive, one possibility is 6x minus 6 could equal 6, or 6x minus 6 could equal negative 6. So if I solve this, I'm going to get 6x is equal to 12. which means x is equal to 2. So that's one solution. And in here, looks like I'm going to get 6x is equal to 0. And if I divide by 6, x is equal to, well, 0 divided by 6 is 0, right? So 0 is another solution. So I get two solutions for that particular equation. And again, you can always go back and check, right? But they will both check in this case. Okay, the last topic I want to mention for this section is solving equations which happen to be in quadratic form. So solving equations in quadratic form. Okay, so what do I mean by that? Well, let me give you some examples first, and you can see why these are all quadratic form. So equations like the following: x to the fourth minus 5x squared plus 4 equals 0. That's definitely not a quadratic equation, right? In fact, it's like it's a quartic equation, right? Because it has a fourth power, but it can be made to look like a quadratic equation with a simple substitution. If I have x to the sixth plus 7x cubed minus 8 equals 0, that's another equation, right? It's a 6th degree polynomial equation, but it can be made to look like a quadratic equation. Or even something like this: if I have x to the 2/3 plus 4x to the 1/3 plus 2 equals 0. It turns out this can be made to look like a quadratic equation with a particular substitution. So I'll say equations like that can be made to look like a quadratic equation with a variable substitution. And if you notice, right, what's similar to all these equations that can be made to look like quadratic equations? Well, first of all, there's 3 terms. So for all these, right, there's 3 terms. And the exponent on the middle term is half that on the first term. And the other thing is the last term is a constant. So the last term is a constant. Okay, do you guys see here? So like this one, I have, in my middle term, I have x squared. So the exponent 2 is half of the exponent on the first term, right? X squared, x to the fourth. And in the last term is a constant. Here, a 3 is half of 6. 1/3 is a half of 2/3, right? 2/3 times a half will give you 1/3. So that's what really makes it so that they're in what's called quadratic form. All right, so how do we solve these? So let's say I want to solve this equation. So again, it's a fourth order equation, but it can be made to look like a quadratic with a simple variable substitution. Usually the letter we give for the substitution of variable that we name that we give is u. So I'm going to let u equal r squared in this case. So that means, remember, if I do r squared, the rule is you multiply the exponents, right? So this is r to the fourth. So that first term is like u squared minus 25, and then r squared is u, so just call it u, and then plus this constant 144 equals 0. So now this is a quadratic equation in terms of u. And that we can solve. In fact, we can probably factor, most of these most of these equations will be such that they're fairly easy to factor. If not, you'll have to use quadratic formula, but let's try factoring. So the only way I can get u squared is u times u. Then I need to think of two things when multiplied give me 144, and when added give me negative 25. That's not so easy. What you might want to do is this. Try factoring 144, and by factoring I mean the prime factorization. So factor this into prime numbers. So remember, to do that you basically used a tree. Start with the lowest prime number, right, 2. Does 2 go into 144 evenly? Yeah, it goes in 72 times. Then I branch off to 72. Does 2 go into 72? Yep, it goes in 36 times. Then I branch off to 36. 2 goes in 18. Then 2 goes in 9, and then 3 goes in 3 times. Okay, so 144 is going to be equal to 2 times 2 times 2 times 2 times 3 times 3. Now, is there any sort of combination where I can get a negative 25? And if you think about it, right, and you have to try different things. Like, you might try, say, like this is like 8, right? 2 times 2 times 2 is 8, and this would be 18. 8 and 18, is there any way I can get 25? No, that doesn't quite work. What about 2 times 2 times 2 times 2? That's 16. 3 times 3, 9. Oh, wait, yeah, that actually works, right? Because if I do negative 16 times negative 9, that gives me a positive 144, and negative 16 plus negative 9 gives me a negative 25, so that works. So I know that this is going to be negative 16 and negative 9. So then I set each of them equal to 0, right, like we normally would do. So one possibility is u is equal to 16. The other possibility is u is equal to 9. But then I have one more step, because remember, u is equal to r squared. So now I have to put r squared here. And if I take a square root, right, of both sides to get r, then you have to remember that it's plus or minus, right? We talked about that last time. So one possibility is positive 4, and the other possibility is negative 4. And then for this one, I do the same thing. Take the square root of both sides. So this was that square root property. And I'm going to get r is equal to positive 3, and then r is equal to negative 3. So really there's 4 solutions. R is 4, negative 4, 3, and then negative 3. So 4 different solutions to that. Okay, let me do one more. Let's say I want to solve this. Equation 3p plus 6 squared minus 3p plus 6 minus 12 equals 0. Okay, this looks complicated, right? However, notice if we do a quick substitution, let's say we let u equal 3p plus 6. Then I just have u squared minus u, right? You can think of this as 1 if you want, minus 1u, minus 12 equals 0. Now it's just a quadratic equation. Okay, let's factor this. So I have u times u. I want two things, and multiplied will give me negative 12, and added will give me negative 1. This you can do in your head, right? Basically, negative 4 and positive 3 will work. So one possibility is u minus 4 is equal to 0, and the other possibility is u plus 3 is equal to 0. So this one will lead to the solution u is equal to 4, and this one will lead to u is equal to negative 3. But again, notice we're not quite done, right? We don't want to solve for u, we want to solve for p. But we know that u is 3p plus 6. So I can plug it in here now. I can say 3p plus 6 is equal to 4. And then 3p plus 6 is equal to negative 3. So in this case, I would subtract 6. I'm going to get 3p is equal to negative 2. Then I'll divide by 3. So one solution is p is equal to negative 2/3. And here I'm going to subtract 6. So 3p is equal to negative 9. And then divide by 3. So it looks like p is equal to negative 3 would be the other solution. And those are the two solutions. And again, you can check them if you want by plugging back in to the original equation. Okay, great. So that's it for lecture 5 on section 2.6.